Okay, yeah, also welcome from my side. We are switching to English now. And yeah, for those of you who don't know me yet, my name is Sebastian. I work with G-Gator, that's an antivirus company located here in Bochum, and we are sponsoring this course since a while. Which basically means we are offering an additional evening event for all of you every time when we have an invited speaker here. And yeah, what does it mean? Basically, after the talk, we will go to my company and there will be some food and drinks and a cozy atmosphere, and it's meant to be a place where we can meet and hopefully have nice discussions. So if you're interested in talking to Sebastian a little bit more in detail about the topics he's presenting today, or if you just want to get in touch with people, especially the more technical people working in the AV industry, then all of you are welcome to join us later. It will, of course, be the possibility to attend when our next invited speaker in January is here as well. So if you don't have time today, it's not a problem. You can take a look at it later on. Yeah, and if you have any further questions, don't hesitate to come to me after the talk, and I can explain it a little bit more in detail. So, without any further delay, let's give Sebastian a warm welcome.
Okay, so yeah, thank you very much for the introduction. I'm Sebastian, and my talk will be on remote timing attacks. So this is obviously a very strange topic in a sense, because you're measuring time and you're breaking stuff just by measuring times. I think there's a huge amount of work where this has been applied, and this has been applied to crypto in most cases. For example, like smart cards and DRM systems and so on and so on. But there's not very much related work. There is related work, but not very much. And you will see which related work I'm citing on measuring or performing timing attacks like remotely on a network. Because a network has a jitter and all the stuff, and you have to cancel out all the noise, and there's lots of noise, and this is what I'm talking about today. Basically, this talk that I'm presenting to you will be somehow a blend of 3 different talks. And all of them were presented or will be presented at CCC, so the Chaos Communication Congress. The first talk was 3 years ago. There I talked about how to perform how to measure exact timings on a network, on a busy network. A year later, so 2 years ago, I talked about how to prevent timing channels, or how not to prevent timing channels, because there's an obvious case where people think you could fix a timing channel, but you can't actually. And also I will give a preview on the talk that I'll give at the upcoming CCC. And this will be on breaking SSL with like certain implementations of SSL with timing attacks. So most of the stuff that is here on the slide, oh, this is German. Oh, so I'm sorry. This is the only slide that is German. So I don't even know what berufen is in German. So I got the job as a professor last year. So I'm in my first semester. Actually, I'm right now on a parental leave. So when you look into my eyes, it's not because I work so much, but because my little boy is sick at home. So I don't sleep at night. Not because of hacking or drinking, but just because of the kid. Well, my research topics are like offensive IT security. So I'm interested in breaking stuff, in a certain sense. So before so basically I studied in Darmstadt and was there. This was like in 2004 or so. I worked there in the Wizard of DOS CTF team. This is like 10 years ago or so. And then I worked as a penetration tester. Went back to the University of Erlangen. Got there my PhD on remote attacks, basically. Actually, 4 years ago, I think I was here in HackPra already, and there I talked on timing side channels and SAP penetration testing. So if you're interested in that, well, you can have a look at that. And all of that I'm only doing because I'm basically my background is a software developer, so I want to write secure code, and I want to teach writing secure code. And in my opinion, you can only teach secure software development when you show them how to break stuff. Okay, this is the Pentagon. The Pentagon is like the this in the United States. There, people think about how to do wars and things like that. Everything is highly classified that goes on in this building, and there's a tiny pizza restaurant around there, a Domino's Pizza. And the guy there, he wrote in an article at Time magazine that he can tell whenever the United States are planning a new war or a new offensive thing or so, which is highly classified. And he said he can predict it several days before they actually start. Then you think like, okay, this is highly classified. How does a pizza delivery boy infiltrate the Pentagon? How is this even possible? And the solution to this is they were just so when the Pentagon is planning a big new project, they work over hours. So they work late, and then they get hungry, and then they order pizzas. And so when you look at how many pizzas are ordered at Domino's Pizza, and when you see a spike that goes to the Pentagon, you know that many people work overtime, and therefore they are planning something. And he was realizing that because he saw this spike, and he was like, okay, it's curious. There's so many pizzas ordered by the Pentagon, and 3 days later they invaded Iraq or something like this, right? And so they got this with several wars. There are several wars started by the United States, and there he saw that there's a correlation, right? So there's a correlation between something that is easy to measure, which correlates with something that is classified. And this is what we call a side channel. Right? So a side channel is something where you have some correlation of something that you can easily measure that correlates with something that is classified, secret in a certain sense. Okay, yeah, pizza. Lots of pizza in the Pentagon, right? They're all fat, I guess. I don't know. Okay, so there are I mean, you guys probably know offensive stuff, right? And there's the CTF team here as well, and so you all guys know SQL injection and buffer overruns and things like that. Those I call invasive attacks because you have a program and there's some type of control flow that was meant and that was compiled by the developer to be performed, right? So there's a control flow that was meant to be executed, and if you perform an invasive attack like an SQL injection or a buffer overflow, you change the control flow of the application. When you have an SQL injection, you change a SQL query. When you have a buffer overrun, you're basically injecting your own shell code, which means you're injecting your own control flow into the process. With side channels, it works differently because you only work on the original control flow. I think you could combine both of these, and there's a combination where you combine a side channel with an offensive or an invasive attack that would be like something like a blind SQL injection, right? So a blind means there's no error coming back. You have an SQL injection, but you don't get the result, and therefore you just check. You check. Does the hash of the administrator's password start with an A? If yes, wait for 2 seconds. And then you're just measuring how long the SQL injection is taking, and then you know whether it starts with A. If it doesn't start with A, you try it whether it starts with B, with C, with D, and so on and so on. And so you can create this correlation for yourself, right? So that's also some type of timing channel, but they're much easier to measure because 2 seconds or so, or 5 seconds, or whatever delay you're programming in, is much larger than like a normal timing channel that you're seeing right now is like in the tens of microseconds, right? That's what we want to be able to measure over a network. It doesn't have to be on a network. So there's various types of side channels that are possible. It could be, for example, electromagnetic emissions. So if you probably have all seen your ATM machines, and even the buttons, they are made of steel. They are made of metal. And one of the reasons is not only that when you hammer on it that you can destroy it, right? But also that the emission doesn't go out. So it's a kind of insulation that you're doing there, because you could formally just stand there with like a few dozen meters away, and you could measure what the guy was typing in because of the electromagnetic emissions. What we're seeing here is an old version of a typo 3, where usually it's classified when you type in a username and a password into a login form. You don't want the attacker to be able to measure whether the username exists or not. So you have like this an error message, something like, okay, username or password or both are wrong, right? Try again, or something like this. And it was really like this in typo 3, but you could tell whether a username exists or not when you looked at the HTTP headers. And the reason for that was typo 3, in order to authenticate a user, they had to find out from the configuration of the user what type of authentication is to be used. Is it only a password, or do you need two-factor authentication, things like that. So they need a username, a valid username, in order to find out how to authenticate this user. And the error that they did was they changed the cache settings of the HTTP request. So they were like, get me the configuration of this username. If the username is there, then change the cache, like the caching. And that's what you see in the headers. And that's the only thing that changes in the response. Everything is equal, right? So that's a side channel that is not timing, obviously, but that is in a storage, right? But you don't see it as well. So it's hidden from you. A user can't tell that there's a difference in these two responses only when you look at the bits and bytes. So you have to look very closely, right? Okay. What is very good when you have a storage side channel is that you only have to measure once. There's no noise or something like this. But you have noise when you measure over the network, right? So let's say there's a timing difference. And that's an abstract example that I'm showing here. So there's some type of side channel, and you have a secret S that can be 0 or can be 1, and you want to hide the fact whether it's 0 or 1 from the attacker. But when you look closely and you measure the timing many times, this is like a histogram of a whole measurement data set, both of these. These are two separate timing measurements. And you see there's a tiny difference between those. So it's not like that you have like one hump over here and one hump over here, and you can graphically tell that there's a difference. That's easy. We're dealing more with something like this. So there's just slight variations. There's just slight variations in the histogram, and we want to measure this. So how do you do timing measurements? And this will be technical. So I really want to tell you right now, how can you do exact measurements? There's one seminal paper by Crosby from 2009, and he did a large-scale timing measurements, not timing attacks, but only timing measurements in Planet Lab. So he created many data sets in Planet Lab and tried to find out how tiny can the delays be that we can still measure over the internet, over a local network, and things like that. And what he found out is that you can measure in hundreds of nanoseconds over a network, which is quite small. But this was an academic paper, and what he used was like a UDP ping-pong protocol. So it's like you send something like a UDP ping to the server with only an integer as payload, and the integer will be interpreted as a time to wait in nanoseconds. So when there's let's say 100 in there, then the server knows it has to wait for 100 nanoseconds. And then he measured the response time until the server sent the UDP response. The good thing was that he had ground truth, so he knew exactly that this particular delay that he just measured is actually 100 nanoseconds, and then he tried to find out with statistics whether they are significantly different or not. So how can you do this? There's many ways of measuring times on different operating systems. Most of them are not very good in measuring exact timings. So most of them are only milliseconds or even microseconds. I think one of the best timers that you can use is an assembly directive. It's called RETSC. There's no C equivalent for this call. So you have to use inline assembler, which I showed over here. And when you call this, it will give you the amount of ticks that the CPU did since it was initialized. Right, there's, I think on the next slide there's something written on there, right? So the good thing on RDTSC, it's tied to the clock speed. So the faster the CPU, the better the precision. That's very good. So when you have a 2 gigahertz CPU, it means you can measure down to half a nanosecond, which is pretty good. But then the bad thing about it is that it's tied to the CPU speed. And the CPU speed varies quite a lot, because you have something like Intel speed stepping, which makes sure that when you don't do anything with your computer, it's idling, that your CPU will be, the frequency will be lowered. And when you have like a 2 gigahertz, 2.5 gigahertz CPU, it will actually run in most of the cases on 800 megahertz or 600 megahertz. Which is a problem, because then the CPU clock speed changes, and when you start a measurement, and then the clock speed changes all of a sudden somewhere in between, and then you stop the measurement, and then you have some number that has no correlation whatsoever with the actual delay. So that's a problem. Power management is a problem. The next problem is process relocation to another core. Most of today's CPUs have many cores, dual core, quad core, octa core. And each of these CPU cores has an own counter of RDTSC. And when both, or when these clocks run on different speeds, which is in most cases possible, so the first core, core 0, is used most of the cases. So this will be the core that runs at the highest speeds, and the other cores tend to run on lower frequencies, and therefore the clocks diverge. So every time when you relocate a process to another core, you might have jumps in these RDTSC clocks. Yeah. And then how do you convert these RDTSC ticks to seconds? This is a thing which you shouldn't care. I mean, the attacks works very good with ticks, but when you write a paper, people want to have nanoseconds or microseconds, so you have to right? And there's no platform-independent way to get the CPU clock speed. You have to read this out. From Linux, there's a special way. From BSD, there's a special way. From macOS and from Windows, and you have to find out which one to get the actual CPU clock speed. Another thing is when you do timing measurements on the same machine, and it's a real machine, then you might get totally different timings when you measure at 1 p.m. or on 2 p.m. because the load on the system changes, the load on the network changes. There might be some scheduled jobs running in the background, and so on and so forth. And let's just say, I mean, every time when you want to measure a delay, you have to have two data sets. One, there's where you try a secret something, and here you try a different secret something like, yeah? And then you want to find out whether there's a significant difference. And it's a very bad idea to just measure 1,000 times with one secret and then 1,000 times with another secret, because the timing might change totally in the meantime. What is very interesting when you're doing timing measurements against a service that is running on Java, Java has this JIT optimization, which means that even after tens of thousands of requests, the JIT optimizer will still reducing the response time. So you have like a slight slope. So the response time still gets smaller and smaller and smaller, even after tens of thousands of requests. So you have to deal with that, and you deal with that by alternating the measurements. So first you measure with secret A, then with secret B, then with secret A, then with secret B. And even that is not the best case. The best case is where you do this randomly, where you do a measurement and you flip a coin and you decide which secret you're using, because you want to prevent something like progressive jitter or something like this. So there might be a different, when you do a measurement with secret A, you might get a different delay when the secret you measured before was also secret A. And the reason for that is caching, right? So when you have two different, when you do measurements with two different secrets, it might be a difference whether the cache has like this part of in it or this part of in it, right? So there's, yeah. So do this randomly. This is the best thing you can do. Then I already said Crosby had like his own protocol. It was an academic paper, so he wrote his own UDP ping pong protocol. But in real time, we want to measure over TCP. So most of the juicy parts of the internet, they run on TCP. And there we have to find some places to start the measurement and some places to stop the measurement. And there's, in my opinion, 3 different places, which I will show here. So the naive approach is you open a TCP connection, you connect to it, and just before you send the request, whatever the request is, can be SSL or it can be HTTP something, whatever. Just before you send the request, you start the timer. Then you send the request. Then you receive the response. Sorry, there's a typo. Oh, I've given this talk so many times, and I've never seen this typo. Okay, so you start the timer, you send the request, you receive the response, then you stop the timer. The problem here is quite obvious. TCP starts with a 3-way handshake. So you have a SYN packet here, an ACK packet here, a SYN ACK packet here, and then you have the ACK package, which will contain the first bytes of the request. Then this will be acknowledged, and there will be a second packet containing the request, and so on and so forth. And then you get the response, right? So here the application is doing something. Then you get the first response byte, you acknowledge this, you get a second response, and so on and so forth. And then you have the tearing down of the TCP connection. So this will be many round trips. And whatever comes on jitter, on noise, with each of these round trips will add. Right? So when you have a UDP ping pong protocol, you have jitter once, because you just have one round trip. And here you have like 20. Or maybe 10, or maybe even hundreds or thousands of round trip, which is very bad because you have lots of jitter. The second idea is you make the 3-way handshake. You send the full request, just not the last byte. So when you think of a GET request, you have like get/http/1.0 /r/n/r, and before you're sending the last /n, you're starting the timer. So you're sending everything but the last byte of the request. Then you start the timer. Oh, there's again. Yeah, then you send the last byte of the request, and you receive the response. Oof, okay, that's good. Then you receive the response, and then you stop the timer, which is good because all the 3-way handshake stuff and the sending of the request and the stuff, everything will be cut out. And of course, we have the assumption here that the application layer that we actually want to measure, where we want to measure the delay, only starts when the full request is there. That's the idea that we have there. And there's one thing that I can still make better, in my opinion, is I do exactly the same as I did in the first place, but I wait not until I get the full request, but only because I only want to have the first byte of the response. When I have the first byte of the response, I know that the application layer is ready, and I can stop the timer. This only works for certain protocols. It doesn't work well with HTTP, because the problem is when you have God forbid, a PHP application. You have a PHP application, then Apache will retrieve the HTTP GET request. It will hand over the data to the PHP application. Then the PHP application will do something, whatever. And if it takes too long, Apache might decide that this is taking too long and will start sending the response headers already. So he will send the response headers asynchronously while he's waiting for the PHP application to finish. So this might work for some protocols, but not for all. Okay, so now you want to do your timing measurement. What do you do? When you do it on Linux, which I would recommend, is you have to disable Intel SpeedStep, and there's another thing there's the same thing on AMD with a different name. I don't know the name anymore. And there's command line utilities. They're called CPU frag, and there you can fix the clock frequencies per core. And the easiest thing is you just set all the cores to maximum power. If it's a 2 gigahertz CPU, you switch all the cores to 2 gigahertz. Then there's another thing that is called CPU C states or sleep states, which means a CPU goes in some kind of sleep state where it doesn't consume as much power. And the problem is the waking up of this takes some microseconds or even milliseconds, right? So you want to disable this as well. This you can do at runtime. You have to boot with idle equals poll as a kernel boot parameter on Linux. Then obviously you want to use wire, so only wired, no Wi-Fi. You want to disable all periodic tasks, so cron has to be shut down. You want to use no GUI whatsoever, everything from the command line. You want to choose your part of the network wisely, which means making a timing attack over the internet is really, really, really difficult. And not only difficult, it might be impossible. And you can spend a lot of time by fiddling out all the noise and things like that. It might be much easier when you want to attack an Amazon cloud computing service or something like this, that you just rent your attacking machine within the same cloud service, because then you're on the intranet, and then you have much less noise, right? So do this wisely, not from hacker conferences, right? And then you want to skip the first few hundred or even few thousands measurements, because the cache is warming up. So when you do timing measurements, you will really see that the first dozens, hundreds, or thousands, depends on the implementation, timings, they go down. When you have a scatter plot, you have it starts very high and goes down gradually, goes down slower. And you want to start at that part where it's basically parallel, running in parallel, which doesn't work with Java, for example, but still. So how do you analyze data sets? Now you have 1 million measurements. It's a CSV file. You open it in Excel, and then you go, so what? What do you do now, right? You can't fill out everything, right? You see lots of numbers. So you need some kind of statistics. And the bad message is that most of these statistics that you've learned in university won't work in analyzing networked timing measurements. This is not the case for other timing side channels. So when you're attacking a cryptographic primitive on a smart card, for example, you might have normally distributed data. So like a bell curve, a nice and clear bell curve. And the thing is also, the central limit theorem says that when you don't have a bell curve, just measure more times. Right? And this works in many cases, but it doesn't seem to work with on networked timing measurements. And this is not only my opinion, but this is also said by Crosby and by other researchers. They found the same thing. They're just not normally distributed. So yeah, these standard hypothesis tests, and hypothesis test is basically the algorithm that you want to use that tells you the binary answer whether there's a significant difference between these two data sets or not. Right, that's a hypothesis test. Okay, Crosby proposed a new box test, and his main contribution in the paper was doing performance tests on all the various hypothesis tests that are described in statistics. He could do this because he had ground truth. So he had many, many data sets, and he knew the exact delay that was used to generate this particular data set. So he could tell when he knew there's a difference of 1 microsecond, but the hypothesis test says there's no difference. Then he was quite sure. Okay, this hypothesis test is not capable of distinguishing these two data sets. So I implemented this box test and published it. So there's a tool, and all the graphics that you will see in the following were generated with this. And I don't have the time to explain his box test, the alternative hypothesis test. So if I'm going too fast, you can look up everything on the video recordings on the CCC on 28C3 and 29C3. Right. So when I'm too fast, I'm sorry, but it's really limited time. But this is really an important thing. I had this example of using maybe a timing attack to distinguish whether a username is there or not in a system, which can be security critical or can be not security critical. The most important thing is when you have a list of usernames to try, and when you do a timing attack, you know you have 50% accuracy. So you do a timing attack, and it will tell you, yeah, this is there and this is not there. Then you know that 50% of the usernames that the measurements said were true, they are only true. So only 50% of the usernames that you found out are actually valid. This is okay for this use case, but in most of the crypto attacks, this is not okay, because there you have an adaptive attack, which means you have many steps and you have to perform many measurements, and you don't repeat the same measurements, but you have to do different measurements. And with the attack that we're going to see in a few slides, you have to do this many 10,000 times or even hundreds, thousands of times. And there the problem is the measurement n+1 depends on the result of the measurement of n. And when you did a mistake in evaluating measurement n, then you have a problem, because all the subsequent measurements will be wrong, and you don't know it. So you can have your timing attack running for days and weeks, and it just won't terminate, and you don't know where the problem was. Right? So there was just a wrong decision. So that's really a problem. So here you have a 50% accuracy, which is better than nothing. And when you have an error rate of 1 promille, that means only 1 in 1,000 measurements will be wrong. This might be already this is not good enough for us, because we need better. Okay. This is how a scatter plot looks like. So this is the first image that you see from my tool. And the data set here, when you look at this, it's like there's no obvious timing difference between the red crosses and the green crosses, right? But it's you have outliers. So there are some measurements take quite long, and there are other measurements which take quite a short time, which is also not really intuitive. So noise, timing noise, is only additive. That means it can only increase the delay that it takes, but it cannot reduce the amount of, it cannot reduce the timing. And so it's very strange to see outliers, but these outliers are found by anyone who's doing timing measurements over a network. So that's strange, right? So you have outliers and you have to deal with them. You have ones that take very long and others that are very short. And then you have something like where you don't know, right? So this particular data set, a scatter plot, is very good in deciding whether there was, whether your measurement setup is good or not. And this here is a measurement setup which is not quite good, because you see these jumps here. You have a small cloud down here, and all of a sudden there's a jump here, and the solid line was formerly here, but it's now here. And the reason for that was power management. So this is a power management kicking in. So here the CPU were running on a high frequency, or was it differently? No, here they were running on a low frequency, because they were okay, don't take me on this, right? But still, so there was some power management kicking in, and this is the result that you're seeing there. And you want to prevent this. So you want to repeat your measurement without these artifacts. But it doesn't mean that your hypothesis test, when you have a good hypothesis test, he can still deal with it. So it's not that when you do a timing measurement on your setup, this is not enough to say there's no timing difference. Not at all. You have to look really closely, and let's look a little closer. What we see here is usually called a box plot or a whisker diagram. And it's called a whisker diagram because usually here you have these whiskers down here. And they are usually standing for the minimum measurement and the maximum measurement. But the problems you have seen is that we have many outliers. So the minimum measurements and the maximum measurements, they don't carry much information. So this is why I chose to display just the whisker diagram or a box plot without the whiskers. And what do you see here actually? In the middle you see the median. The median is when you order your data set in ascending order, for example, then the measurement right in the middle, so you have 100 measurements, you order it, and the 50th measurement will be the median. And then you have the 50% percentile and the 25th percentile. So this is what you see here, right? So we have basically filtered the measurement. And what we see here is there's a difference. It's a tiny difference, but you see that both boxes are slightly skewed, just slightly. And we could only see this because we removed away these whiskers which contain these noisy outliers, right? Then we have a third way of displaying it. It's called the cumulative distribution function. And the way to interpret it is, you see this here is 1.75. So here we have 1.6 and here we have 1.8. And this might be 1.75, which means that 75% of all the measurements are in this part. And it also means that they are below this timing boundary. So this is this is time, and this is the probability that they are in there. And it means 75% are below this timing here. And all the stuff that you see here are only 25% of all the measurements. Yeah. And now, when you have a uniform distribution, that means every timing has an equal probability of appearing there. Then it would be like just like a diagonal line. And there you already see it's not really, it's not a uniform distribution, obviously, because it's highly skewed. So what can you see here? You see, it's not a perfect match. So both data sets don't have a perfect match. There's they're still overlapping in all the places, but there are areas where they are overlapping more, and there's other areas where they are overlapping less. And this is important for configuring your filter. So it basically means here you have a total overlap, which means in these percentiles you don't have any information. You don't see, you can't distinguish one data set from the other, but you have around the 40 percentile and something like the 90 percentile. There you carry information. There you have this like where both separate slightly. And when you look at this, you know how to apply your filter. So you know which measurements carry more information than others. This is only for analyzing it graphically, right? That's a graphical way of analyzing it. There's also a way to analyze this with algorithms, and my tool supports this as well. Basically, what I did is I implemented a Crosby's box test, and Crosby's box test works on this kind of graphical representation where it just looks where both data sets overlap and where they don't overlap. And it focuses on these parts where it doesn't overlap because it carries most of the information. Okay. So how do you prevent timing side channels? What do you think? That's a question for the audience. What's the intuitive way? And you're all feeling it, yeah?
Timing safe compares.
Sorry?
Timing safe compares.
Timing safe compares. So that means, yeah, when there's a delay because you did something wrong in the programming, and you just fix the programming, so there's no timing delay anymore.
For example, in a string compare, checking every jar before returning and
Yeah.
not aborting after the fifth jar is wrong.
Yeah. So something like this, that's a timing channel. That's a very basic timing channel. You have a decision. You do thing 1 when the parity of secret is 0. And here you do some other thing when the parity is not 0. And the idea here is doing thing 1 has a different timing than doing thing 2. That's pretty clear, right? And so what you just said is we fix it by doing something that is like a constant time. So we could just do both things. They will be done every time. And depending on the secret, we just use result of 1 or use result of 2. And here we have the assumption that using the results is timing constant. This is your idea, right? Okay? All right, okay. And this is the proper way of doing it. The wrong way of doing it, and many people think this works, is like adding a random delay to it. So we just fix everything by by putting some noise on the channel. So the problem that we have here is it's slower because we're doing always both things. We don't do thing 1 or thing 2. We do both things. Then it's timing. The timing is constant, obviously, but it's slower, right? So it's easiest to remove the timing side channel from the code. But what if you don't have the code? You don't know. You don't have the know-how for fixing it, because the example that I showed right now was trivial. But fixing a timing side channel in a source code can be very difficult, because you don't know what the compiler is making out of the out of the source code. So it could be that the code looks like constant-ish in a way, but the compiler generates totally different machine code, and there you have a timing channel. So this could be a possibility. What are the different ideas of fixing a timing leak without fixing the source code? The first, like the atomic way, if you want, to fix it like a timing side channel, is you pad your response time always to your worst case execution time. And finding out the worst case execution time is also non-trivial, but let's just say you can find it out. You measure all the possibilities that the process has. You take the maximum amount of time it took, and then you like pad the response time, or let me put it this way. You get a request, you do something in there, and there's a timing channel in there. After a certain time, you see that your process finished, but it only took them, let's just say, 45 microseconds. Then you will wait 105 microseconds in order to pad the delay to worst case execution time. This fixes timing side channels totally, because there's just no delay anymore. Whatever you do with a process, you always have constant timing. The problem is it's not usable anymore, right? So nobody can do this. Nobody can afford to do this. There's random delay padding, and this is very easy to implement, because you just get a random number and wait this random number. That's basically it. So it's just 2 lines, what you have to do in your source code. There's something like this. Very easy. And here I have a random delay. And the problem is, when you look at both data sets, before the random delay padding and after the random delay padding, you still see there's a difference. And it might be not that obvious anymore. So it might be that it's like a bit skewed or things like this, but the timing difference is still there. And it just puts some more burden on the attacker to create better filters. That's everything, right? That might not be the best idea, but still, even very smart people think this might fix timing attacks. So, like most of you guys, you guys might know Dan Kaminsky, so he's very, very famous. And he had this idea of putting a random delay on every packet on an operating system level. And you can easily do that on Linux. It's really very elegant if you think about this. So TC is a Linux command, and with this you can modify certain parameters of your network stack. And with this call, you will add a random delay between 3 milliseconds and 1 millisecond on every packet that goes out of the interface ETH0. It's very easy. So I actually implemented this, and I put a few files on a web server and downloaded them. I started with 1 byte, and I finished with 10 megabytes. And I measured the time it took for me to just download this from the web server. And you see, the bigger the file gets, the more time it takes. So there's almost no, this is the normal delay. And, this is without a delay. And this here are the measurements with the delay. And you see, you have like an increase in the time it takes to download this file from the web server, about 7 times, 10 times. For the bigger file, it's only double the time, but still it might not be worth it. And then I used my tool and tried to find out, does it really prevent timing channels, right? Does it really work? And the measurements or the results of this are displayed here. This delay that you see here is like the timing delay that we want to measure. So it's here we have a random delay between 3 milliseconds and 1 millisecond, and this is the timing delay that the attacker really wants to measure. And I started with 10 nanoseconds and then just doubled it every time. So it's 20, 40, 80, and so on, until I was at around 5 seconds or so. this is the amount of measurements it took me without the delay of this that we added here in Linux. So in order to distinguish an 80 nanoseconds delay on a local host, on a local machine, I only needed 31 measurements. And starting from 160 nanoseconds, I was okay with 16 measurements. So 60 measurements were okay in order to decide that there's a delay, yes or no. Then I added the random delay. And there you see here that I couldn't distinguish 18 nanoseconds anymore. I couldn't distinguish 2 microseconds anymore. But starting with 5 microseconds, I was already able, with just 4,000 measurements, to distinguish both data sets. And then it gets a little noisy. Here we see a little increase, but starting with 300 microseconds, I could already distinguish this delay with just 16 measurements. Right, so we have like a performance decrease about 7 times, and it will fix some of the timing attacks, but not all of them. So 5 microseconds would be enough to break the SSL implementations that I'm going to show you in a few seconds. So this doesn't work, right? Don't do random delays. This is just bullshit. Okay. Now that was like the part that I've already showed a few years ago. Now let's just switch to the new stuff. This is joint work with a lot of researchers from University Bochum. Tibor Jager, Juraj Zimorowski were part of it, Christian Meyer and so on, Jörg Schwenk. And we had this published at Usenix Security this year. And this is supposed to be like not an academic presentation, but more like from a hacker point of view, right? So how can you really create a tool so that you can break SSL? Well, I probably don't have to tell you that SSL got a lot of attention in the last years, right? So 2014 was really crazy. We had Heartbleed, GoToFail, we had Poodle, so SSL in version 3 is totally broken. And in the years before, we saw different things. So many attacks against the same protocol. Yeah, right. Because when you look at it, the protocol itself doesn't look very complicated. So when you look at a textbook TLS implementation, you just have a few steps, a bit of RSA, a bit of symmetric encryption, and then you're basically finished, right? So you just have a client hello, you have a server hello, the server sends you your public key, the client creates the session key, the pre-master secret, encrypts it with a public key, sends it over to the server decrypts this pre-master secret with his private key, and then they have their session key, and then they can communicate on a symmetric level, right? So that's actually quite easy, but when you look really closely to the certain parts, it's really incredibly difficult to make a proper implementation in TLS. And why is that? We had a few design decisions in the 90s that are right now that showed to be very bad. And one of the decision was to use a padding style of the standard PKCS1. Why do you have to use padding? So RSA is a block cipher. When you have a public key with 1024 bit, you always have a blob of your. So you only can encrypt clear text and ciphertext in 1024 bit, right? So you always have these. You always have this block size, and the symmetric key that we will generate it by the client is only 46 bytes. So it's not 48 actually, because these will be always the same. This is the protocol number, and this random part here is the pre-master secret. And so you have to do some padding when you want to encrypt 46 bytes with RSA. You have to use some padding, some type of padding. And this was used in PKCS version 1.5. The thing that they created there was it has to start with a 0002. Then there's some random padding which must not contain a 0 byte, because the 0 byte is used as like the cutting part where you cut the padding and the real message to be encrypted. So everything after the 0 byte here will be the content that you want to actually encrypt. Well, it's not a bad idea. It's very easy to implement and things like that. Actually, quite straightforward. Okay. You probably have all seen how RSA is encrypting and decrypting the data. What is important to note here, and this distinguishes it from symmetric ciphers like AES, for example, which does this weird substitution, XOR thing, and so on. RSA works with integers. So it's just a very big number. It's not a bit field of 1000 bit or 2000 bit or 4000 bit. It's really just an integer that is very large. And that is important. That's the first thing that is important. And the second thing, and I will go into this a little deeper in the next slide, RSA is malleable, which means when I give you a ciphertext, then you don't know what the clear text is, but you can make changes to the ciphertext that will lead to predictable changes in the clear text. Right? That's a property which is actually quite bad for a crypto algorithm. Yeah, so right, but you need these two. So you have an integer and you have the fact that RSA is malleable. In 1998, a guy called Daniel Bleichenbacher came up with a very cool algorithm, and he was able to break the SSL implementation of these days. And now I want to look into the way how he did it. So basically, he created an algorithm where an adversary who is in possession of an RSA ciphertext, some RSA ciphertext, he can recover the plain text of this ciphertext just by getting him an oracle. And this oracle does two things. It takes an arbitrary ciphertext, decrypts the ciphertext to the plain text, and doesn't reveal the plain text. He doesn't give out the plain text. He will only tell whether the format that he decrypted was conformant to PKCS1. So to the format that we had seen here, and I think I'm going to show this later on. Yeah, I'll show this later on. Okay. So it decrypts the ciphertext and it responds with a 0 or 1 whether the padding that was used was valid. Nothing else. And I can't go into the details how the actual algorithm is working. I just want to give you the idea how it's working. Remember that PKCS1 starts always with 0002. And also remember that RSA is always an integer. And when I get an information that something is compliant with PKCS1, I know that this integer is has a certain boundary, because it is the leftmost numbers of this integer start with 0002. So I can make a boundary on this particular integer. And when I mix this with like the malleability property, I can basically send a ciphertext to the server. The server tells me whether the padding was correct or not, and then I can slightly, with each and every request, I can decrease the possible range in which the clear text can be. Right? So let me just repeat this once more. RSA, the RSA encryption theme is integer-based. So you have an integer. And when you have an oracle that gives you the information whether or not it's PKCS1 compliant, then this means that the integer of the clear text has a certain boundary. And these are like the number 2 here and the number 3 here, because you know it starts with a 0002. So it doesn't start with 0003, and it doesn't start with 0001. It starts with 0002. And now you have the malleability, and then you can learn basically the range in which the clear text can be, and you learn the range, you can reduce the range in which the possible clear text can be with each and every request to the oracle. It was called, Bleichenbacher's attack was called the million questions attack because at his times he required 1 million Oracle requests to decipher like the pre-master secret. Okay. I said that we need an Oracle that tells us whether the plaintext starts with a 0002. This is in a perfect world. This is an Oracle that would be really perfect. The problem is TLS implementations, they do more. I said there's non-zero padding over here. So there are SSL implementations that will check that in the non-zero padding is not a 0. Right? Then it might also check whether the 0 byte is on the right place, and it might also check this 0301, which means it's protocol version TLS 1.0. So there are many checks that can be done, and the more checks that are done, the smaller the strength of our Oracle, which means, let's say the attacker has created a ciphertext which deciphers to a clear text that starts with a 0002. But there's somewhere here in these 205 bytes, there's a 0 byte. And therefore, the Oracle will tell me, no, this is not PKCS1 compliant, even though it starts with a 0002. So the strength is reduced by each and every check that the SSL implementation is doing. Right. Okay. This basically this is just a bit of related work. So the Bleichenbacher attack can not only be applied to SSL. There are other protocol designers who made the same mistake of using RSA with PKCS1 in version 1.5. For example, there's a standard called XML encryption. And with XML encryption, you take an XML file, you take out a piece of it, so just a subtree part of this XML document, then you generate a random key, encrypt this small part with AES, for example, and this randomly generated key. Then you encrypt this key with a public key of your receiver. You put the encrypted key over here, and the data you put this here, and you can basically break this with a Bleichenbacher attack, right? So we did this against XML encryption with Juraj Somorowski and Tibor Jager. That's a paper from 2012. And the interesting part is the people keep doing the same mistakes over and over again. So there's a new draft, I think it was in 2012 or 2013, that is called JSON Web Encryption, which is basically the same as XML encryption, only applied to JSON. And what did they use? RSA with PKCS1 in version 1.5, which means Juraj had like a day off, and he was really bored, and so he took our attack scripts that we used against XML encryption, so that they worked against JSON, and broke the first implementation hours, or let's say just a few days after it was first released. So there's a standard, there's the first implementation of it, and he breaks it within days because they just keep doing over and over again the same mistakes. And these were just the timing measurements. I skip over this. So what do you do to counter this Bleichenbacher attack? The problem is most of the ciphers that are used in today's SSL and TLS implementations that are based on RSA still use PKCS1 in version 1.5. So the protocol basically is still vulnerable, and it was never fixed. You could, for example, use ECC, so elliptic curve cryptography or things like that, which is not susceptible to Bleichenbacher's attack. But still, I think many still use these RSA ciphers. So how did they choose to fix it? So basically, they said the protocol is still susceptible, but they wanted to prevent the creation of a Bleichenbacher oracle. So they wanted to prevent that someone can find out whether the PKCS1 encoding was valid or not. And this is how they did it. This is the description in TLS 1.2, which is the most recent TLS generation. What they do here is they generate a random pre-master secret on the server side. And they do this all, like every time they do this. Then they decrypt the ciphertext, and in line 3, they do all the checks whether it's PKCS1 compliant. So does it start with 0002? Is in the non-zero padding really no 0 inside and things like that? If this is not the case, so if the padding is indeed wrong, then they won't throw an error. They will just continue with the randomly generated pre-master secret, which leads to the fact that the client has a different symmetric key as the server, and it will, at some later stage, it will just fail. Right? So TLS will break down the protocol because both can't talk. They just decrypt gibberish. But this error message is indistinguishable whether the PKCS1 encoding was compliant or not. Now this is the most recent part. In the former TLS standard descriptions, they had it slightly different. There's just a slight variation to this, and we exploited this. So TLS 1.2, 1.0 and 1.1, they use a different approach. They decrypt the ciphertext. In line 2, they perform the PKCS1 compliance checks. And only if the PKCS1 encoding was wrong, they generate a random pre-master secret and use this. Right? And then we speak about timing channels. This is a difference, right? So there must be a difference between this part and this part, because here you're creating, you're getting random bytes, cryptographically secure random bytes. And we measured this in C, and it takes a few microseconds. So it takes a few microseconds to generate a few random bytes in order to get this pre-master secret. Does anyone have an idea why they did this formally? Do you see the reason for this? Why they chose to do it that way, and later on decided, oh, it might not be a good idea because there's a timing channel in there. But do you see the motivation why they did this? Yeah.
Let's say performance.
It's performance. Absolutely. So when you like reducing the performance of each and every TLS handshake, even if it's not malicious, and most of them are not malicious, just for a couple of microseconds might not be acceptable, right? So because SSL implementations are highly optimized. So then we did a measurement setup. So we had a Bleichenbacher attack module, and this will keep generating ciphertexts for us, and like meaningful ciphertexts. And this is the measurement module. This is based on a framework that was created by Christopher Meyer. He recently graduated with a PhD, and he's now in the industry. He wrote everything in Java. And this was like a mess. Oh my gosh! Because we tried to do timing measurements, and it was really, I mean, I love Java, but it's just not capable of doing timing measurements because we had so much noise in there. So this was impossible. So I looked at other TLS implementations and wanted to reuse them, and then I looked into the OpenSSL code. And this is really a very strange API, and I understood nothing. That's really the problem. I didn't even know whether it's single-threaded or multi-threaded. So it's really, I couldn't tell from the API. A big mess. So I don't want to blame OpenSSL on this part because I wanted to do different things that they were not intended to, right? So there's no API in OpenSSL that allows you to do like timing attacks against SSL, right? Okay. Okay, so I don't want to blame them for this. But there's a very tiny TLS implementation that is open source. It's called NITROX SSL, and they really just they open a TCP port, they have writes and reads in there, so everything that I just wanted. So it was really perfect. And so we did a patched version, so I patched NITROX SSL, which now just takes whatever PMS we want to send over the channel. It just takes this and gives us a number, and the number is the delay that it took for the processing. So this was our measurement setup, and these are the results. We found 4 side channels in 3 different implementations. Not all of them are exploitable in the past. And so I will tell you how everything worked. So the first was an error message. So this is not a Bleichenbacher channel through timing, but through an error message that was thrown in the TLS implementation of Java. So when you want to open a TLS server in Java, you can do this. And JSSE is written in Java. So it's a totally pure Java implementation of TLS. And they had some programming error in there. I don't want to give the specifics, but if I gave some very weird-looking pre-master secret to the server, it would just trigger an internal alert, and this internal alert was not caught. It was an exception that went uncaught, and this led to not a protocol failure, but like a Java failure, and which you could tell just by looking at the error message. So that's a straightforward 1998 Bleichenbacher attack. No timing involved, and it allowed us to break the pre-master secret with 170,000 requests within 12 hours. And interestingly, with a bigger key, it took us shorter. So here you have like a bigger RSA key is actually less secure, and the reason for that is you need to have this weird behavior. I can't go into the details. Either this is a 1024-bit. There you have a tiny area where this particular thing has to be. In 2K keys, you have like this area and this tiny area, and in 4000-bit you have like this big area, and here again this tiny area. So this internal error area is bigger with the bigger keys. But it's just an implementation specific thing. This is not right. So it's 4000-bit keys are still more secure, I'd say. So this is fixed, obviously. Then we looked at OpenSSL, and OpenSSL still does the old TLS 1.0 and 1.1 version of it. So they are generating the PMS if and only if the PKSS1 encoding was wrong, which we could measure. And you see a timing channel here. It was very good, not much noise, but the problem was OpenSSL is very strict in checking what is a valid PKSS1 message and what is not a valid PKSS1. So the oracle strength was very weak, which means we have a very tiny chance of a clear text starting with 0002 to be detected as PKSS1 compliant. Right? So only 1 in 10 to the power of -8 clear text that start with 0002 will be detected as PKSS1 compliant. And that means we would need like 10 to the power of 12 requests in order to break the PMS over TLS, over OpenSSL, which is not possible in reality. But it's still fixed, so the timing leak is also fixed in OpenSSL. So that's good. We had the third channel, and I said that the code quality from OpenSSL is really a matter of discussion. Let's put it this way. Let's be polite, right? So they did a really good job, but you can tell that there are when you look at the code, it's not nice, but when you know about all the background and the pitfalls that you can get into when you implement TLS, you probably know why the code is looking like it's really looking right now. The TLS implementation of JSSE is really nice. It's a textbook object-oriented way of implementing TLS, which meant we could break it with just 18,000 requests, because exception handling is really very expensive. So it's very time-consuming. And so if we could trigger the right, like they have like bad padding exception, something like this, and we can measure this. It's around 10 microseconds, depending on the Java virtual machine. So there's a difference between 1.5, 1.6, 1.7, and so on and so on. But still, we could break it. So that's a very strong oracle. Even though the code looks very nice, it doesn't perform a lot of PKSS1 checks, right? So it's actually bad. The code is looking good, but it's not very good way of implementing it. The fourth channel, and this might be the worst that we found actually, is in a hardware accelerator. So you can buy cards that do TLS termination for you. So you have like a TLS stack implemented in hardware for performance. And the people that are using this are people who have a lot of requests coming in. So it's basically a load balancer, a big machine that you put, an appliance that you put in front of your firewall, and it will terminate SSL and just speak clear text with all the like load balancing machines. And Juraj looked at this, so we have in the lab upstairs, there's I think an F5 big IP and IBM data power, and he did some measurements, and it behaves very strangely. You see, it's very optimized in a sense that it doesn't check 0002 at the beginning, but it only checks something 02. Which is weird. I mean, I told you, performance is a big thing in SSL, TLS. The problem that we came in is Bleichenbacher's algorithm doesn't work with this anymore. So we need 0002, because I explained already to you, then we have this boundary. We don't have this anymore with when we have something 02, but we could extend Bleichenbacher's algorithm so that it will also work with this. The oracle is not very strong, but it still leads to the fact that after 4 million queries and 41 hours, we could also recover like the pre-master secret of these connections. Okay, which brings me to the summary. The interesting thing that you should learn is timing attacks. When you have a timing delay of just a few microseconds, you can do this in a local network. Right? So when you have a local LAN, let's say a DMZ or so, or a cloud environment, something like this, this works quite well when you have a single-digit microsecond delays in TCP connections. And I should mention, many cloud providers are using exactly these things that I showed you in the first slides. They disable power management and things like that because they want to have high responsiveness. Right? So it obviously takes some time for a CPU with a reduced frequency to scale up, and they don't want this, so they have like their CPUs running with full power, which is good, right? This is exactly what we want. We have bad designs in cryptographic protocols, and I should to excuse these people that it wasn't really known in 1995 or in the 90s that there are the protocol decisions that were taken during these days that they might taunt them for decades afterwards. So this is what I already said. RSA and PKCS1 in version 1.5 is just very difficult to do right. It's actually broken and you can fix the implementation, but this is very fragile. This should be clear after looking at all the TLS implementation. And then we have a concept which is called MAC then encrypt, which means the message authentication code where the integrity for of the messages are checked. It's within the clear text. So basically the client takes the clear text, makes a MAC over it, puts a MAC over it, puts this MAC to the clear text and encrypts the whole thing, which has the drawback that the server first has to decrypt everything in order to get the HMAC out. So he doesn't know whether the ciphertext was tampered with or whether the integrity of it is valid or not. Before he can find out the integrity, he has to decrypt it. And this is basically what we're doing, right? So if the integrity check would be the first thing that would be done with each and every message that is sent, then Bleichenbacher's attack would never have been possible. And many of the other bugs that I've shown you in the first slide, all of the padding oracle attacks in the first slide, would have been prevented by MAC then encrypt. So it's much better to use a different thing, which is encrypt then MAC. There's actually an extension to SSL these days. It's a draft, and I've shown the link here as well. And there you take the clear text, you encrypt the clear text. So you have the ciphertext. You make a MAC over the ciphertext and send both to the server. And the server doesn't have to decrypt. He can just check the MAC over the ciphertext and decide whether the ciphertext was tampered with or not. Right? So, and then you're right. And implementing TLS really is a minefield. So I always thought, like 2 years ago, I thought that TLS is pretty straightforward. But now looking at it, it's actually quite difficult. So, and this might be the case for most of the protocols if you just look close enough. Right? TCP also looks very easy on the first hand, but then when you look deeply, it's very difficult. Okay, thank you very much.